today we want to study finding the absolute maxima minima of two variable function on a region. So essentially we studied two methods so far. First method we studied is the second derivative test. So there we need there we have a domain of the function and we find the partial derivatives exist inside domain, and inside domain we find what are the critical points, and there we study uh, the second derivative test. So inside region basically we apply the second derivative test, and on the other hand we studied the Lagrange multiplier method. So whenever we are given a function which we want to maximize or minimize on the boundary of the set, right? So there we studied Lagrange multiplier method. So what we'll do here is now we are basically combining both of these methods. So the question will be given function f of xy, which we want to maximize or minimize inside the domain, points inside the domain as well as on the boundary. And since we will include the boundary, it is similar to the condition of the closed interval AB. So that is what we discussed in the last lecture, the one variable case. So there we have function which is continuous on the closed and bounded interval. Then the minimum value exists at the end points, that means at the boundary points or at the critical points, right? So this method of absolute maximum minima we want to extend today for two variable case. Let us write down the main points. So if we have a function so f of xy be a function whose partial derivative exists on the given region. So region means there is a set which has a boundary. So such a set is known as a region. So it includes all the points inside that boundary as well as on the boundary. So this region D is bounded by some curve. So that curve we are the equation of the curve we are denoting by v of xy equals to 0. So in last lecture we have seen that whenever we have such a equation x square plus y square equals to 1, that is a unit circle, and unit circle the equation itself is v of xy is equals to 0 in this form. So that is this boundary curve basically of this given set, and to find absolute maximum minima of the function f on the region D, what we do, we first find, so method is same as this one. So first we find all the critical points, and then first we find all the critical points, and then we find all the value of the function at the endpoint, right, at the boundary point. So what we'll do is we will first find all the critical points of the function f which lies inside D, right? So f is a function which may be defined on a larger set also, but basically we are concentrating on the points of the domain only, not the outside domain. So we will first identify what are the critical points inside domain, which is a region, and secondly, after that, we shall apply. So inside the region, we already found all the critical points. So now we have to focus on the boundary, and we know that for the boundary we apply the Lagrange method. So we shall apply Lagrange multiplier method on the function. So function is f of xy, which we want to maximize, minimize, subject to the condition that our points xy will lie on this curve, on this boundary. So this is basically the procedure how to find absolute maxima minima of the given function on a region, and that region is bounded by a curve which gives us equation g of xy equals to 0. So this is the procedure to find all the points which are critical and at the boundary. Lagrange multiplier method will give some points. So finally, what we do is to find maximum minimum value. We compare this value of the function at those points. So interior to all the points interior to D and all points xy which is coming from Lagrange multiplier method. We find value of the function, we compare value of the function to find absolute maximum minimum. So essentially this is what the method. So let us see one example. So we are looking at find the absolute maxima of the function. So we are given function f of xy equals to x into y. Alright, this is two variable function. and the region we are given is B equals to all the points xy which lies on the circle as well as inside circle, right? So we want to find all the maximum, absolute maximum values, the unique absolute maximum value of this function. So what we do first, we will first find the critical points of the given function. Right. So what is the, first of all, what is the boundary of this region? So this region is basically all the points in the xy plane such that x square plus y square less than or equals to 1. So this is essentially this set. X square, this is a unit circle, x square plus y square equals to 1, and all the points inside this circle, that is less than 1, right? X square plus y square less than 1. So this is our region with the boundary. So note that boundary of D boundary of the region D is the unit circle. So equation is x square plus y square equals to 1. So therefore what we get, the equation of the Lagrange multiplier method that corresponds to this curve, that corresponds to the boundary. So therefore what we have is, therefore g of xy we will take based on this equation, whatever equation we are getting depending on given region. So given region is x square plus y square less than equal to 1. We got the boundary x square plus y square equal to 1. That means our g of xy is x square plus y square minus 1 is equals to 0. So first we have identified the boundary of the given region, and that gives us the function g. So now we are starting this procedure. So what is the first step? First step is to find all the critical points. So let us find out all the critical points. So step 1 is find all critical points of the function f of xy which are interior to the given region, right? So in this first step we are just finding critical points of the function without looking at the boundary, because we are interested in the points interior to D. So that means x square plus y square less than 1. So there is no role of g in the first step. So let us find out all the partial derivatives, first order partial derivatives. So here note that our function is f of xy equals to x into y. So the first order partial derivative of fr fx equals to, so f is x into y, so fx is y, right? And fy is x. So therefore for the critical points we consider fx is equals to 0 and fy equals to 0. This condition gives, so So fy is y, that means y is equals to 0 and fy is x, so it is x equals to 0. So we get these two equations. So therefore we get only single critical point, that is 0 comma 0. So therefore we get the critical point 0 comma 0. There is no other critical point of the given function. So what we will check here is it should be interior to B. So our region is x square plus y square less than or equals to 1. So interior to it, that means x square plus y square less than 1. So clearly 0 0 is interior point of B. So therefore we got a critical point which is inside B. So that means our first step is over. So what was the first step? First step was that finding all the critical points of the function which are interior to the given region. So we got one point which is interior to given region. So let us now apply the second step. So step 2 is Lagrange multiplier method. That is we apply the Lagrange multiplier method. So in the first step we found all the critical points inside D. Now we want to find all the critical points on the boundary of the region. So boundary of the region means we are applying the Lagrange multiplier method on the function over the boundary, and so boundary means we are considering all the points on the boundary which is x square plus y square equals to 1, right? So we need to solve this problem basically to find all the critical points on the boundary. So once again, to apply the Lagrange multiplier method, we need to check the gradient of G is non-zero on the points of the curve. So this, let us write a remark that note that the gradient of G, so that is basically Gx Gy, and so this is two variable gradient. If we have a three variable function, we have a Gx Gy Gz. So for two variable functions, we know that partial derivatives are 2x and 2y with respect to x and y, because our g equation is x square plus y square minus 1. So, so note that this is not 0 on the points of the unit circle. Because if this is 0 vector, that means x is 0 and y is equal to 0. That means xy is origin, but origin is not on the unit circle. So that means we can apply Lagrange multiplier method. So what is the Lagrange multiplier method? We know that we need to find all the points xy such that gradient of f is lambda gradient of g, and another equation we have is g of xy equals to 0. So that is, we have equations. So our equations is fx equals to lambda gx, fy equals to lambda gy, and g of xy equals to 0. So again, this, if you substitute the value of the function here, then fx is y, lambda times gx is 2 times x, right? Because g is x square plus y square equals to 1. Similarly, we get the second equation by partially differentiating f and g with respect to y. And the last equation is unit circle equation, that is x square plus y square equals to 1. So we need to solve these three equations, and we have to find all the possible values of x and y. So what we'll do is, we can either convert x and y in terms of lambda, that is one way, or we can so in any method, either we use elimination. Suppose we have a linear equation, we can use elimination method also, and solve the equations. So what shall we do here to solve this equation? So what we have is y equals to lambda 2x and x equals to lambda 2y. So we can convert using equation 1 and 2. Either we can convert in the equation of y or in the equation of x. Right, so let us substitute that. So substitute x equals to 2 lambda y in the equation y equals to lambda 2x. If we do this, then we get equation of y only. Alright. So what we get is we have the equation y equals to lambda 2x, in which we are substituting x equals to 2 lambda y. That means it is 4 lambda square y. So finally we get 1 minus 4 lambda square y equals to 0. So now we have two cases, because multiplication of these two numbers is 0. That means either that means 1 minus lambda square is 0, or y is 0, or both of them is 0. So let us start with the, suppose if in the first case we have y equals to 0, then we can use the equation of the circle, and what we get is, we get value of x to be plus or minus 1. Why? Because x square plus y square is equals to 1. So in this case, we get points xy which satisfies all this equation are x is plus or minus 1, y is 0. So this was the case y equals to 0. Now the second case is one minus 4 lambda square is 0. So that is 4 lambda square is 1. Hence we get the value of lambda to be square root of 1 by 4, and both the values. So that means plus or minus half, right? So this is what we have as a value of lambda from the second case. We got two cases, out of which first case we discussed. The second case is this one, in which we are getting lambda is equals to plus or minus half. So now what we can do is we know the value of lambda and we have these three equations. So if we substitute the value of the lambda, then we get some relation between x and y, right? So if lambda is plus or minus half, then we get y to be plus or minus half times 2x. So that is y equals to plus or minus x, right? So from equation 1, what we get is we get y is equals to plus or minus x or x equals to plus or minus y. So now finally we have the equation of g that we use usually to find value of x and y. So the equation g is unit circle. So that means x square plus y square equal to 1 will become x square plus, if y is also x square, then this is 2x square is equals to 1. So that means x square is half. So x is plus or minus 1 by root 2, right? And the relation between x and y are their sign is either same or opposite, right? So x value is 1 by root 2 and y is either 1 by root 2 or negative value. So therefore we get points. So points are 1 by root 2. If x is 1 by root 2, y is same sign, it is this point. If x is 1 by root 2, y is negative sign, then it is minus 1 by root 2. Similarly, the other 2 points, if x is negative. So you can see that all these 4 points lies on the unit circle, right? So essentially it satisfies the equation of g. So what are these 4 points? These 4 points lies on the unit circle and their solution to this problem, which is finding either maximum or minimum value of the function. So earlier we got one point that was origin, and now we got these 4 points, which are the critical points lying on the boundary of the circle. So finally, to find absolute maximum minima, what we do is we have to evaluate the function at all these points which we are getting. So for that, usually we make a table and evaluate value of the function at every point xy. So our function is simpler in this case, which is x into y, and points are 0, 0, 1 by root 2, 1 by root 2, minus 1 by root 2, minus 1 by root 2, then opposite sign of x and y. So clearly the value of the function at origin is 0. X into 1 for this point is half. Here also it is half. And for last two values it is minus half. So these are the critical points and value of the function at those points. So
Hello, sir.
yes,
Sir, my connection was lost. Can you repeat from that case lambda is equals to plus minus half?
lambda equals to plus minus half. Yeah. So lambda is equals to plus or minus half. So we just substituted lambda equal to plus or minus half in the first equation. The first equation was y equals to lambda times 2x. If we substitute lambda is equals to plus or minus half, then half and 2 will cancel out. So we get y equals to plus or minus x. So that we have substituted y equals to plus or minus x. That equation we are getting basically from equation 1, and then we have used equation number 3. So if we substitute y equals to plus or minus x in equation 3, then basically what we get is we get all the possible values of x. So they are plus or minus 1 by root 2, right? So using lambda equal to plus or minus half, we have found value of x, and then if we know value of x, we can find value of the y which lies on the unit circle. So they are these values. So we know y is plus or minus x, and value of the x is plus or minus 1 by root 2. So that gave us these 4 points. So these 4 points lies on the unit circle. So they are basically critical points for the function f, which lies on the curve unit circle. The 1 by root 2, 1 by root 2, and all these 4 points. And the points which are inside interior to the domain that we already found in the first step, that is 0, 0. So now we have evaluated the function x into y at all these 4 points, all these 5 points, and by looking at the value of the function, we can see that maximum value, absolute maximum value is half, absolute minimum value is minus half, and at 0 we have nothing. Right, so these 2 points are basically absolute maxima. And these 2 points are absolute minimum. And at 0, neither absolute maxima is there nor absolute minima is there. Right. In fact, you can take it as an exercise to show that at 0 we have actually saddle point. Right, at origin this function has a saddle point. So you can find along a particular curve passing through origin, you will get value of the function is 0. The value of the function is greater than 0, and along some another curve passing through origin, you will get the value of the function is greater than 0. Two curves where along one value of the function is greater than 0, along one is less than 0, that means it is a saddle point. So this was regarding one example which how to find absolute maximum minima for two variable function. So any doubt so far in this particular example?
No, sir.
Okay. So then I will take one more example, that is regarding three variable function. How to apply the Lagrange multiplier method. In fact, the Lagrange multiplier method can be applied for more than three variables also mathematically, but it is usually easy to find for multivariable function. So if we have two functions having continuous first order partial derivatives, we want to find maximize or minimize f of xyz equals to the function f of xyz subject to some constraint which is g of xyz equals to 0. So if the gradient, so here also the gradient should be non-zero on at each point xyz on the curve satisfying g of x naught y naught z naught is 0. If this condition is satisfied, then in this method we solve the following equation. So equation is the same, which is gradient of f is equals to lambda times gradient of g, and g of xyz is 0. But here the gradient is slightly different because we have a three variable function. So f and g are three variable function. That means gradient is fx, fy, fz is equals to lambda times gx, gy, gz, and final equation is the given surface. So here the equation in three variable, that means it is a surface. The equation in two variable is a curve like circle. And then we find the value of the function at this all these possible points which satisfies this equation. So let us see one example. So find a point x, y, z on the plane. So the equation of the plane is 2x plus 3y minus z equals to 5. So this is my z. I write z in this way, right? It looks like 3, but it is z. So I use this notation. So find a point x, y, z on the plane which is near to the origin, right? Which is nearest to the origin. So basically what we need to do here, let us do in the next PDF file that what is the question? Question is to find we want to find the point on this plane which is near to origin. So that means we are finding basically the distance between x, y, z with the origin. So distance function of x, y, z with origin distance between these 2 points is square root x square plus y square plus z square, and our point x y z lies on this surface, right? So that means basically we need to find basically minimum distance. So we need to find minimum value of square root x square plus y square plus z square subject to the equation of the plane, that is 2x plus 3y minus z equals to 5. Now this function is in terms of square root x square plus y square plus z square. So if square root x square plus y square plus z square has minimum value, x square plus y square plus z square also has minimum value at that point, right? So finding minimum value of the function square root x square plus y square plus z square or x square plus y square plus z square is same thing. So therefore what we do is we find we find minimum value of the function x square plus y square plus z square. So this function we'll call f of x y z, which we want to minimize subject to the condition v of x y z equals to 0. So this equation gives 2x plus 3y minus z minus 5 is equal to 0. That gives us the constraint basically. So now gradient f equals to lambda gradient g. So we can see that gradient g is non-zero on g of x y z equals to 0. Alright, because the gradient is 2, 3 and minus 1. 2, 3, minus 1. And that vector is always non-zero vector. So this is other than 0 vector on the whole surface. So therefore we can apply Lagrange multiplier method, and we have these two equations to be solved. So therefore if you substitute the value of the function, we get 2x equals to lambda times 2, 2y equals to 3 lambda, and 2z equals to minus lambda. So these are three equations coming from the gradient condition, and the last equation is equation of the plane, that is 2x plus 3y minus z minus 5 is 0. So in this case it is very easy to solve these equations, because directly we will get the value of the lambda, that will substitute and we will get the value of x, y and z. So what we get is x is equals to lambda, y is equals to 3 lambda by 2, z equals to minus lambda by 2 from the first equation. So therefore 2x plus 3y minus z minus 5 is equals to 0 gives. So just substituting these three values in this equation, what we get is 2 lambda plus 3 times 3 lambda by 2 minus lambda by 2 is equals to 5. That will gives us 2 lambda plus 9 lambda by 2 plus lambda by 2 is 5. So essentially we get 7 lambda is 5. And now we know the value of the lambda, which is 5 by 7. The substitute we get value of x, y and z from this equation. Alright, so therefore x is equals to lambda, which is 5 by 7, y equals to 3 lambda by 2, which is 15 by 14, and z equals to minus lambda by 2, which is minus 5 by 14. Right, so we got x, y, and z values which minimize the given function. Right, so basically note that the distance between the minimum distance between point on the plane with origin. So here we started with the function which was x square plus y square plus z square, but finally we want to find it's at the square root of x square plus y square plus z square. That means at square root of the function f at this point. So the final answer is square root of f of value of x is x by 7, 15 by 14, and minus 5 by 14. So finally, we can compute these. This turns out to be square root of 350 divided by 196. So this is basically the answer of this question. So local maximum minima, we are not going to study the second derivative case for three variable case. Only we have I have taken one example of three variable case function when we can apply the Lagrange method. Okay, so any doubt?